So before I go into PCA, this is a kind of a more of a geometrical approach. So let me start with some basic measures that we would be using. So one of the most common measures is variance. So variance along x is going to be, for example, if I take the 0, right, variance along x from the mean. So this is 2, this is 2. So 2 square plus 0 square plus 2 square. Got it? By 3. Likewise, variance along y. Likewise, this same set of points also. So both the variances are same, but are the points same? No, right? The variance along both are same, but we cannot say there is definitely a difference between these two sets of points. So how do I differentiate that difference? So that's where comes the concept of covariance, where covariance is said to be the product of coordinates. So when I have the concept of covariance, I will be able to relate the similar points even more better than what I did with variance. So variance, I may not be able to catch this relationship between the points. So with covariance, by going for the product of the coordinates, -2 into 1 is -2, 2 into -1 is -2. So these two are of the same covariance. So I happen to group them together, right? So this concept of covariance is what we will be using in our principal component analysis. So when you have the covariance, now you happen to see that these points are much related to each other rather than these two other points going equal to each other due to variance. So now what is covariance? How are we going to use it? So we see three sets of points over here. If you're going to compute the covariance of these points, and you'll be getting the total covariance of the right side points to be positive and the left side to be negative, and the covariance of the middle one is going to be 0 or it's going to be very small. So this covariance, and you will also be confusing now yourself with something called correlation. Correlation is a standardized form of covariance, right? Correlation value varies between -1 to +1, where towards +1, the maximum is +1, it shows positive correlation, and 0 to -1, where -1 shows negative correlation, right? So what is this covariance matrix? So covariance matrix is a kind of a relation between two variables or points in a two-dimensional space or any n-dimensional space. So it is, what is a covariance? It's actually the product of the coordinates of a point. So covariance of a matrix, covariance matrix is going to represent the all the values of the data set. Suppose we want a relation, a transformation of some set of points to another, right? I want you to just understand the math or the concept of covariance in this application. I will come to why this transformation is occurring and why do we need it when I teach the PCA algorithm, right? So assume that I have a set of points like this spherical manner here, right? And I want a transformation as such as this, right? So how does this look like? I'm going to transform these points just by pulling the points along some direction, right? I'm having this small thing here and I'm trying to pull this small thing along a direction, right? A kind of pulling a paper, or in image processing, you call it a shearing and kind of operations, right? So if you want to do that, if you have a linear transformation, now what do I mean by a linear transformation? I have the covariance matrix of those set of points, right? 9, 3, and 4, 4. Now using that covariance matrix, I have a relation, right? This relationship is called as my transformation relationship. So plugging these values, 0 to 0, 0 comma 0 will come over, 0 comma 0 here, 1 comma 0 is this point. So when I plug it over here, I'll be getting 9 comma 4 that goes over here. Yes. And then 0 comma 1, 1 comma 0, this is the second point, and next is 0 comma 1, this point over here. 0 comma 1 goes to 4 3, so it's somewhere here. 4 3 minus 1 comma 0 goes to -9 -4, that's over here, and last one obviously goes over here. So you see that this kind of a transformation is what I call a linear transformation. So what was in a kind of a spherical form, got transformed to a kind of an ellipse, right? And this transformation of two variables is what I call it as a linear transformation. So as I told you, you can imagine this transformation which has two vectors that are being stretched, or two sticks that are being stretched in a different direction. So I'm taking those two sticks to be as 2n 1 and minus 2n 1, which are orthogonal to each other. Two vectors, right? 2n 1, two. So these are two unit vectors that are going to be stretched along some value. So the first vector, that is a red vector, this red vector on the left is going to be stretched for 11 units, and this green vector is going to be not going to be stretched. Okay, it's going to be kept as it is. That's how I get my eigenvectors. That is the direction in which I am going to stretch, and the next one is the magnitude of the direction, how much I am going to stretch in that direction. So this stretch or this transformation is what that gave me the linear equation in the previous slide for that change from a set of points in this domain to a set of points in another domain. So now this eigenvectors and their respective values is called my eigenvalues, right? So this covariance matrix, or the basic vector that I had, into some vector, into some other vector with a value, which I call it as eigenvalue, is what is going to give me my stretch. For a given matrix, how do I calculate the eigenvectors and eigenvalue? You take the characteristic polynomial, you multiply the diagonals, right? You find the determinant of the matrix, and for the determinant, you get the quadratic equation, and you take the roots of the quadratic equation, and you substitute the roots, and you get the eigenvalues. So this linear transformation from one domain to another is what we are going to use for our PCA. Why I need this? Assume I have a set of points. I have a set of points, right? Now, the variance across of these points across the x-axis is, assume some value 1. And the variance across the y-axis is also value 1. So how many dimensions is this set of points? 2 dimensions, right? So I'm going to talk about dimensional reduction. I want to reduce the dimensions. So which dimension should I choose among these two so that I will get the maximum information? What do I mean by maximum information? I should be able to capture the most of the information that is represented in that set of points. In sense, I need to capture the entire variance of the points, right? So if I happen to reduce by this axis, x-axis, then I may end up in a lot of multicollinearity. What do I mean by that? The same points will be overlapping over the same points, right? So I need to find a transformed space where I will be able to capture the variance among these points in a more better way. I need a transformed space. I need a transformation, clearly. So this is where I'm coming to the concept of transformation. So assume that if I have a plane like this, I'm going to have a plane like this, then definitely the projection of these points on this plane would capture a much greater variance than this. Projection of the green points on the red plane will be better than the projection of the points on their original axis or the original planes like X or Y. Suppose I am going to produce these points here, project it on the x-axis. The variance will be some 3 units between all these points and the mean of this point. I hope you remember how we computed variance. If I'm going to produce along y-axis, again the variance of these points from the mean along y-axis, this is the mean along y-axis, yes? So along y-axis, it doesn't produce a much difference. The variance will be the same. But if I have a line as this red line, right, more of the points will be uniquely projected. If I take the projection of the points on the x-axis alone, I'll get some few points here. And some points will be overlying on the other. Same is the case for y-axis. I'll get some points will be overlapping on the other, some points will be multicollinear and so on. But if I'm going to project it on this plane, which is completely correlated with that, then I'll be able to get a very good projection. Now got the point? What am I going to do? A data set that had two features, feature 1 and feature 2, I'm going to transform it to another domain by a transformation followed by a projection, by which I'm going to retain only this one feature or this only one value. I'm going to produce it only on a one dimension. So my two-dimensional data set is going to be converted to a one-dimensional data set, whereby I will be able to capture the most of the characteristics, features of the data set. So now, if I want to do a classification or a grouping or a prediction, which one would be better? Using only x1, using only y1, or this transformed plane, which will serve me as a better tool for doing some decision analysis on the data. I don't want two-dimensional data. I want to reduce it. So which axis should I take? X or Y or the transformed data? Which one will you choose? Transform, because it shows you the maximum amount of characteristics, features of the data in which it intends to represent, right? So if you want to do a classification, you can do even better way, more than doing it over here, because you can't get the information back. It is a kind of a lossy information transform, but it ensures that most of the data is found, or you get most of the data. I hope now you got the concept of why we need a linear transformation and how it is happening here in PCA. Now let's go to the derivation. Suppose I have a set of points. What do I observe here? The variability across x1 and variability across x2, or the variance across x1 and x2 are somewhat kind of similar, right? Variability across x1 and x2 are similar, and x1 is correlated with x2. So when I have this, I want to transform this to another domain whereby so in the transform domain, the same set of points are going to look like this. Yes, when you tilt it, the same set of points is going to look like this. So now the variance of across Z1 is much greater than variance across Z2. Our motivation is we need a mathematical model to transform a correlated set of points to an uncorrelated set of points. What have I done here? I had a set of points along x1 and x2, and I'm going to transform it to some other domain, right? How do I do the transformation? Like what you saw in that PPT, a kind of stretching kind of thing. Instead of stretching this side, I'm going to stretch these points over to another transformation. I need a transformation where the variation can be captured to the maximum level. So we need a math model to transform a correlated set of features to an uncorrelated one. Why do we need this in kind of data mining applications? Can you give me an example? I don't want the attributes to be correlated among each one. Why do I need that? I don't want the independent variables to be correlated among each. For example, if I have height, weight, age, and date of birth, right? Age and date of birth are going to be perfectly correlated. Whenever the age increases, date of birth also increases. That is very sure. Leave it. So let's take the example of height and weight. That is also going to be somewhat correlated, right? Other than outliers and exceptions, like me. Okay. So otherwise, it's going to be as height increases, generally weight also increases. It's going to be a kind of a. So when you want to make a decision, you can think of giving up height or weight. If you want to calculate the some index, you can think of giving up height or some components you can give up. So you don't want the independent variables, features to be correlated among themselves. If they are correlated, you can remove them. It is a kind of redundant thing. You know that when this is also increasing, this is also going to increase. So why do you need the knowledge of both? Not needed. Right? That is what is the intention. And we are going to see how we are going to get this transformation. So you have all my blue points over here, right? So consider a point. Let me say, sure, this point, which is x1 and x1 comma x2. So this is along the initial axis, and it is tilted to another transformed plane, right? Z1 and Z2. By tilting it over, I am tilting the x1 and x2 over an angle theta. Over an angle theta. Now I call this point M. So if the data point M is projected on x1, data point M is projected on x1, what do I call? I call it, what will be the projection here? What will the projection of M on x1 be? M1 is going to be x1 comma 0, and projection of M on x2. The angle between x1 and z1 is theta. The projection of m1 on z1. The projection of m1 on z1. What will it be? This is x1, right? This is z1, right? And this is tilted about an angle theta. This is my point m1. Projection of m1 on z1. What will this be? What is cos theta? Adjacent by hypotenuse. So it's going to be x1 on cos theta. Right? Projection of m1 on z1. Likewise, projection of m1 on z2, projection of this is m1, right? And likewise, you have m2 over here. Projection of m2 on z1. Right. So if this is theta, this is also going to be theta because it is opposite angles, right? So we get four projections like this, right? Projection of m1 on z1, m1 on z2, m2 on z1, m2 on z2. So we get four projections like this, and the four projections will turn out to be on z1. We are going to add those four projections. So at the end of the day, we are not going to use sin theta or cos theta, but it's good you know if you understand that and know it. Okay. So now this is the transformation. From the x1 domain, I have got to the z1 and z2 domain for 1 point. Got it? z1 and z2. What will be my transformations on z1 and z2? Now, how do I write this? On generalizing this, I would write it like A transpose X. Now, what is this going to be? This A transpose is going to, Z is this vector. A transpose is going to be now this is what I have represented in this form. Is this representation clear? How I came up with such a representation? How I transformed x1 and x2 from the xy domain to z1 and z2 domain? Yes. Now this is a kind of transformation. Now we will prove how this transformation is orthogonal. Why it needs to be orthogonal? The two vectors should be perpendicular to each other. Remember that green and red vector. Green and red vector, but both are stretched at different values. With stretching yield you, what are the values? The eigenvalues. What are the vectors? The eigenvectors, right? Let's see how you come to that also. You'll have that also here. So these things, I will generalize it as, since this is the A matrix, I'll take it as A11, A12, A21, A22 for our two variables, x1 and x2. This was the initial domain. X1 and x2 are our attributes, and the small x1, x1, x1 are different values in x1 and x2. Like how we have x comma y. So likewise we have x1 comma x2. So the variable name can be x1, x2, like how we have x and y, right? Okay. Now generalizing this whole expression here. So if you have two variables, it's going to be x1, x2 to z1, z2. If you are going to have z variables, how will it be? So p variables, z equal to ax is going to be, z1 is going to be a11, a12 up to a1p. This would be the generalization. right? For any data set, to transform it to another data set, you had a covariance matrix in that slide. You remember? Likewise, you have a transformation which is this. How did you get this transformation? Why is this transformation needed? To increase the representation of the data. A data which was uncorrelated so and so, to bring it to a different axis where the variance of the data can be captured in a better way, you need this transformation. Got the point? So how do you prove that this is orthogonal? Now this is my transformation, right? Cos theta right? So this is A1 and this is A2. Yes, am I right? This is A transpose, right? So when I write it as A, I can call it as A1 is going to be cos theta and sin theta. So A1 transpose of A1, what is it going to be? Cos theta, sin theta. This is the transpose of A1. From here I am making it to this A1 transpose A1. So this is going to be cos theta, sin theta. So cos, sin, what will be this equal to? Sin square theta plus cos square theta. So likewise you can check out A2 transpose A2 will also be equal to 1. Similarly, if you apply this for the entire thing, A transpose A, what will you get? Identity matrix. What does this mean? Why do you need orthogonal transformation? To ensure that you get the maximum variance of the data set. Okay. So I want to maximize the, now again I'm going to map it to eigenvalue and eigenvector. How do I come there? I want to maximize this is my goal, right? I can transform to any number of any domain, but I want it in such a domain that which axis will give me my maximum value. Like if I have my data like this, I can transform this any number of domains. And if you happen to have more than one variable, x1, x2, x3, x4, x5, I will equivalently have the transformation to also be in z1, z2, z3, z4, and z5. Yes or no? Here I had x1, x2. After transformation, I got into z1 and z2. Right? Now in this z1 and z2, which captures maximum? Z1 captures the variance across so much of data, but if I'm going to capture the variance across Z2, it's going to be only this. So I will not take the value or values represented on Z2. I'll omit Z2 and I'll go only with Z1. That is my dimensionality reduction. So if I have x1, x2, x3, x4, and x5 n-dimensional data set, when I'm going to transform it, in the transformed space also I will have so many variables. But I want actually the dimensions which capture the maximum variance, right? So for that, what do? I need to ensure I capture the maximum variance. So in order to capture the maximum variance, we need two values, mean and another is the covariance along of the data. When that mean and covariance of the data is not available, right? we take a sample of the data and we calculate the sample mean and sample covariance, right? When you have a huge data, you are not able to calculate the mean and covariance. Then you take a sample mean and the sample covariance of that data. Each principal component, Z, that is my transform, Z1, Z2, Z3, and so on, is a combination of X and some associated transform. So, what is the condition? First principal component, that is Z, is associated with the transform A1t of X, subject that A1t, and which maximizes the variability across, which maximizes the variance. So this is for the first principal component. Likewise, the second principal component will also have A2t of X is to maximize subject to the condition A2 transpose A2 is equal to 1, right? And covariance of A1 transpose X and A2 transpose X is 0. That means it captures the maximum variance, right? So my maximization is going to be maximize variance of Zj subject to the constraint the involved vectors Aj are orthogonal, or the same constraint I can write it as clear. How will you solve this? Maximize or minimize, right? Let's go by using Lagrange. So Lagrange, I introduce the Lagrange variable L, which has the covariance Lagrange variable S Aj subject to the condition right? Maximize Zj. What is Zj? Subject to the condition this, right? Where do I get this? Right? Maximize this subject to, this is the Zj I have written over here, and subject to this condition is given over here. How will I solve this? Differentiating this with respect to Aj, what will I get? Differentiating this with respect to Aj, this becomes 0, and so this becomes lambda because this is a scalar. 2 gets cancelled, and aj pulling the both the 2's get cancelled, pulling the aj out. S minus lambda I is equal to 0. Now what does this look like? Characteristic equation. Yes?
Yes, sir.
It has p roots. And you can solve this using, and lambda is the eigenvalue. Got this? Able to correlate with how we got the transformation, right? And why the transformation is orthogonal. Yeah. So that the what I pictorially showed on the slide, the math and the geometry behind this is this, right? So obtaining a suitable value of lambda by solving that eigenvalue and eigen equation, right? S is going to be a P cross P matrix. What is that? The covariance matrix. Covariance matrix of the data. And which one will you choose? Which vector will you choose? So for each vector, Z1, Z2, Z3, Z4 or principal component, you are going to have a corresponding eigenvalue. Lambda 1, lambda 2, lambda 3 and lambda 4. Which one will you choose? Z1, Z2, Z3 you have. Among the Z1 to Zn, which Z will you choose? Having maximum variance. What is the variance? The eigenvalue is the variance. Then you are calculated the eigenvector and the eigenvalue. The eigenvalue that gives you, that maximizes the variance, is the vector which has the maximum eigenvalue. Right? So you have transformed x1 and x2 to z1 and z2 to some value, and you will get the vector among the in the transform space, that which has the maximum eigenvalue is what is going to have the maximum variability of the data represented. Simple as that, right? So if you have some data, right, you are going to have different transformations. The transformation that has the maximum eigenvalue would be the one that has captured the maximum variance. How will you choose between these components? So by capturing Z1, I'll get so much of information, maybe Z2, another set of information, right? So now it's up to you. Out of Z1 and Z2 or Z3 or how many ever components you have, you can take the relevant components. Z1, which has the maximum eigenvalue, you can set a threshold on the eigenvalue. You can rank the transformed vectors based on their eigenvalues, and you can omit the vectors with lower eigenvalues. By that, you will be getting a few number of dimensions in a transformed space that represents the data in an efficient way. Yes, agreed. So what is principal component analysis finally? You have a large set of data. I have 5-dimensional data here. I have a 5D plot for which I calculate a covariance, which is going to be a 5 cross 5 matrix, right? After capturing covariance, I am going to calculate the eigenvector and the eigenvalues of that covariance matrix. If it is a 2 cross 2, you can do it. 3 cross 3, you can do it by hand. More than that, you'll have any online tools or even scientific calculators you can enter and calculate the eigenvalues. Rank the eigenvalues, right? And then you choose some amount of the values that are a bit high. Either you choose 3 or 2, that depends upon you, depends upon your space constraint and all, right? It's like you are transforming a 5-dimensional data into 2 dimensions that captures the maximal information of the data. I hope this picture conveys it to you. A 5-dimensional data you are capturing into, now see, does this picture convey this? Initially, you saw it as a 5-dimensional data, but now on 2 dimension itself, the entire information is being captured almost with some loss, right? So this is enough. Like how we had for 2-dimensional data, even if you remove 1 dimension, we are having the entire information. For 5-dimensional data, even if you remove the fresh 3 dimensions, you are having the two, the colored one, the green and the red one. It's going to reveal almost all the information of this 5-dimensional data set. So this is what PCA all about. So given in a 2D plot, you will have the same 5 cross 10 cross 5 table into 10 cross 2 table. I hope now the entire picture is clear. Yes. So you have one solved example. I have put it here. You can check it out. Like given a data set, how will you calculate? So the first step is you find the covariance of the data. Find the covariance matrix, and then get the eigenvalues and the eigenvectors of the covariance matrix, right? And using that eigenvalues and eigenvectors, rank the eigenvectors based on their eigenvalues, and choose the top 2 or top 3, whichever you want. By choosing 1 or 2 eigenvectors, you know how the. So I choose V1 and V2, that is these 2 vectors alone, and I plot all the 5-dimension points on that. I'll be getting the reduced data here. Okay, you have this video, you can watch it whenever you want.